In this video, we'll discuss how to implement simple linear regression in R, both by hand and using built-in functions in R. First, I'm going to load up the library BSDA, which is a package from a textbook that incorporates some fun datasets. The one I'm going to be using today is a built-in R dataset into this package called NFL Draft with a capital N. Doing $NFL draft, or in general any dataset name, you can see what some of the details of that dataset are. So in this case, I can see that this dataset has three different variables: rating, 40 time, and the weight of some of the top offensive linemen in the 1994 NFL draft. What I'm going to look at today is to see if weight is related to 40 time using a simple linear regression. Now first I'm going to investigate my data. So I'm going to just do head NFL draft. Now what you can see here is that for every individual, their rating, their 40 time, and their weight is given. And recall how in our lectures we discussed how important it was that for every person or every individual or every case, we called it, that all of these numbers were correctly paired. If these numbers are not correctly paired, I can't do a simple linear regression validly. One of the things that can be tough for some students to get is to understand which variable is the independent variable and which variable is the dependent variable. And often it depends on how you ask your research question. In my particular case, I want to look at how weight can affect or is related to 40 time. Now the normal way I would ask that question is, does weight affect 40 time? That requires an experiment to conduct because the word affect is causal, and recall that we can't make causal claims in an observational study. So instead, I'm going to ask, is weight related to 40 time? But even though I'm asking is weight related to 40 time, I can mentally identify, I think weight is going to have an impact on 40 time. And I can't say that in my research question because I can't make the causal claim, but I can mentally understand that. That is, I think weight may predict what the 40 time is going to be. I think weight might have an effect on what the 40 time is going to be. So, if weight is going to impact the 40 time, weight is going to be my independent variable or my predictor. The 40 time is going to be my dependent variable or my outcome. So weight is going to be X, 40 time is going to be Y in all of the equations we've talked through in class. Now one of the first steps that you should do is to plot your data. So plotting your data is a really good first step to make sure that you're fully understanding what that data is, fully understanding the patterns that are going on in that data. Just like in correlation, simple linear regression assumes a linear relationship. There's going to be a more complex definition of linear coming down the line, but for simple linear regression we're looking for a line, so we don't want to see a curve, something like a quadratic up or down, don't want to see any S's, any weird circle. We just want to see something that somewhat resembles a line. In this case it's not super clear, but it does seem like, yes, this could have a line where as weight increases, 40 time increases. And note that I'm getting this from my visual image, and I expect you to be able to look at your visual images and to be able to make some of these intuitive conclusions. Another intuitive conclusion that you may come to is that, does this make sense? So thinking about the weight, if I'm a heavier person, is it going to be harder for me to run 40 yards fast? And the answer is probably yes, that we would expect as weight increases for the 40 time of these offensive linemen to increase. So we would expect this to be a positive relationship. Now to calculate the parameter estimates by hand, I'm just going to use the equations that we had in our notes. If you need to double check them, I highly recommend going and pulling those up and looking at them and seeing how this code connects directly to those equations. I'm going to have x minus the mean of x quantity times y minus the mean of y quantity, and add all that up, and then divide by the sum of x minus the mean of x squared. And recall that this was the sum of squares of x, y divided by the sum of squares of x. Notice that I did x and y here. You don't have to. You could just use the weight column from the NFL draft dataset and the 40 column from the NFL draft dataset by itself. But x and y are much shorter to type, so it's worth my time to write this line where I can just use a single character instead of having to retype all this every time I want to use the letter X. Also, it makes my code nice and flexible in case I need it. Now in this case, what I might do if I'm showing my work is I might show Dr. Florin, here's my B0 and my B1. I do this later in the code. But if you're doing this for homework, this is a good step to show your work. You can either do that or, as we've demonstrated before, by wrapping the intermediate pieces of your code in parentheses if you're doing intermediate pieces in a single line. Now we've already done AB line in a previous R video, but now let's look at a little bit of the documentation. AB line adds straight line to a plot, and it has a whole bunch of different things that we didn't look at last time. Specifically, it has the arguments A and B, which can be the intercept and the slope. So if I'm looking at adding my value, recall that B0 is the intercept, that would be A, and B1 is the slope, that would be B. And now I can do AB line using my custom created regression parameters and see how this line fits. This is pretty neat, as using these formulas we have found the perfect line to fit this data. This doesn't mean that all of the dots are going to fall on this line. This does mean that if you drew any other line on this data, that the dots would be further away on average. That is, their errors, the distance between the dot and the true line, or the residuals, the distance between the dot and this observed line that we have from our 50 data points, or however many data points we have, that would be larger. This is the line that gives us the least amount of error in this data set. So this is the very, very best line, and we found that using just this little bit of code, and we're able to draw that onto our plot. That's pretty cool. Now there are built-in R functions that can also calculate these parameter estimates. So if we use the LM command, LM stands for linear model. So we were talking about a simple linear model. Now we're going to calculate a linear model. In a previous video we talked about the function notation, how on the left side is going to be our y variable, on the right side is going to be our x variable, or on the left side is the dependent variable, the right side is the independent variable or variables. In this particular case, you'll note that I'm using 40 and weight without the dollar sign. In formula notation in LM and plot, we're allowed to do that as long as at some point we give it the argument data equals and tell it what data set we're using. So this knows that I'm going to look for the 40 variable and the weight variable in the NFL draft data set. We can see that the intercept and the weight are printed by default. Now note, some students get confused. This weight doesn't mean that the 0.003 is itself a weight. Recall what this value is. This is the slope. This is the slope. So as weight increases by 1, this is how much the 40 time increases. Looking at B0 and B1, I mentioned these were down later. We can see that to rounding error, these are exactly the same as what the built-in R system tells us. And again, I want to remind you one more time that this weight value is not referring to the weight at all. It is the slope. It is the slope. So this value and these units are in terms of the outcome, in terms of 40 time. On that note, let's go on and try to interpret these values. So recall that our interpretation of B0 is the intercept. So if you had a weight of 0, your 40 time would be 4.175 seconds. That's the statistical interpretation on average. However, meaningfully, we know that nobody has a weight of 0, so this actually doesn't really mean anything, and we can talk about how to center this variable in a moment. The slope, however, is particularly meaningful, and how we would interpret this slope is for every increase in weight by a single pound, the 40 time, on average, increases by 0.003 seconds. What this means to me, and I look at the sign, this is positive, so as your weight goes up, your 40 time goes up, and 0.003 seconds is a very, very, very small increase. So as your weight goes up by a single pound, there's a very, very, very small increase in 40 time, which kind of makes sense. If you're only a pound heavier, your 40 time shouldn't jump by 5 seconds. Thinking about this, we can interpret this. Think about if you gained 100 pounds, what would happen? Well, if you gained 100 pounds, you would go up by 100 of these. So that would move the decimal back 2 places. So increasing by 100 pounds would mean that you increase your 40 time by 0.3 seconds, which does seem to make sense that your 40 time would go up by at least a little bit if you increased in weight by 100 pounds. In fact, I'd be surprised if it only went up by 0.3 seconds if you put up on another 100 pounds of weight. Finally here, we're going to look at the linear model that we made. Now we can save this as mod. It's a variable with the linear model, and if we type in mod, this gives us that same output. But if we save this linear model as a variable, it lets us do other things with it, such as put it in a B line. We can draw a line of this linear model. Now I'm going to color it red because hopefully it's going to go right over this black one, and we want to see if it does anything different. But we want to add the line from the linear model onto our plot, and we can see that this black line gets completely covered up because the black line, that is our hand calculations of what the best fit line is, and this red line, that's ours calculations of what the best fit line is, are identical. One last thing that maybe we'll do is we'll create an x-centered variable to demonstrate how we would center the x variable. We'll have x minus the mean of x, and recall that this is the weight, so we would just have NFL draft weight minus the mean of NFL draft weight. And then we could rerun the linear model. I'm going to do it with y and x centered just to demonstrate. Notice that the slope did not change at all after centering x, and this is an important property of centering x, is that the slope doesn't change, and our interpretation for the slope doesn't change. What does change, however, is our intercept. Our intercept is very different, and the interpretation changes. The previous interpretation of the intercept is that when, for an individual who weighs 0 pounds, on average, their 40 time will be 4.175 seconds, which was a ridiculous interpretation. In this interpretation, after I've centered x, what we would say is for an individual who is the average weight, their 40 time on average would be 5.225 seconds, which is a much more intuitive and helpful interpretation. So in the case when my interpretation of beta 0 does not have a meaningful interpretation, I can center my x value to get an interpretation of beta 0 that actually is helpful. And again, in this case, the interpretation would be for an individual of average weight, we would expect their 40 time to be 5.22586 seconds. This has been a video demonstrating how to implement simple linear regression in R, including how to center variables and how to do some basic interpretations.